start recording. Okay, well, happy Friday, everybody, and it is it's week 8 Friday, and we only have 2 weeks left in the quarter, which is kind of crazy to believe, but but yeah, and in this class I give the final exam on 10th week Friday, so really that's it. 2 weeks from now, you'll take the final, and then it'll be see you next quarter. So anyway, it's just coming down to it. Okay. Today I wanted to spend some time reviewing intro stats, and so I kind of informally pulled the last lecture, and I said, who took basically intro stats at UCLA, stats 10, stats 13, something along those lines at UCLA versus, who took it, like AP stats in high school or stats at a community college or something like that. Most students had not taken it at UCLA. And so I am not sure of the kind of what quality of intro stats people got. And so, stats 10, they fit a decent amount in 10 weeks, a little bit less than the AP stats curriculum. I mean, the AP stats curriculum spans the entire year. And also, at the community college, it varies from one school to another. So it's hard to know. So anyway, I'm going to try to fit pretty much all of the stats 10 curriculum into one lecture today. So in about 50 minutes, I'm going to try to cover as much as I can from stats 10, just so that we're kind of all on the same page when we go into next week, where we'll cover randomization tests and bootstrap tests and kind of these sampling-based hypothesis tests for statistical inference. And so I kind of just want to make sure we're all on the same page regarding p-values and all of that. So I'm going to kind of blitz through all of this. I hope it's an okay review. If you have any questions on anything, don't hesitate to interrupt me. But if it also all feels like review, then that's actually a good sign, because it means you've learned your intro stats material well. So I think, probably your very first week of intro stats was spent just being able to describe data. And you learned things about like how to describe the center of a distribution by using the mean and the median. And depending on your curriculum, you might have talked about how to find the mean, how to calculate the mean. You add them up and divide by how many you have, or you have, find the median, you find the middle number, and you can kind of just start from the outside and work your way in. And that works, but conceptually, it's important to know that the median, both of these things are kind of balance points, okay? The median balances the number of values, or the number of points that are lower than the median, and the number of points that are higher than the median. The mean, on the other hand, balances the deviations or the distances of the points that are lower with the distances or the deviations of the points that are higher. And because the mean is trying to balance the deviations or the distances, it's going to get pulled in the direction of any kind of outliers or the skew. So if you have outliers that are way bigger, your distribution is skewed right, and your mean will get pulled in that rightward direction. If you have outliers that are way lower, your mean is going to get pulled in that direction. And because the mean is affected by outliers, we often prefer to use the median to report the center of a skewed distribution. Kind of a classic example is, a college, once bragged that, their alumni have a mean earnings of, $120,000 per year or something, okay? And the truth was that pretty much everybody did not make that much money, maybe, something a lot more modest for the mean earnings. But one of their alumni had gone on to become this successful millionaire, making millions of dollars each year. And that brought, that skew brought the mean to be something much higher, to something a little bit unrealistic, okay? So here's just a little bit of a picture. This is just a very simple data set, six values. The data set values are 1, 2, 3, 4, 10, and 10. And I've plotted them as these little black dots here, 1, 2, 3, 4, 10, and 10. And you can see that the median, which is this line in blue, balances the number of points. So you got 3 points below the blue line, or to the left of the blue line, below the median, and 3 points above the median, okay? And we can see that I could take these points at 10 and 10, and I could just move them even farther away to say like 100 or 1,000,000, and the median would still remain at this spot, okay? That these values, all that matters is that there's 3 on this side and 3 on this side of the blue line. The median balances the number of points. Whereas the mean in red, it has to balance the distances, okay? And so the mean is at 5, and the distance from 5, 4 is 1 unit away from 5, 3 is 2 units below 5, 2 is 3 units below 5, and 1 is 4 units below 5. And 10 and 10, they are both 5 units above 5. So you've got 2 observations that are 5 units above 5, and you've got observations that are 1, 2, 3, and 4 units below 5. And so if you add up 1, 2, 3, 4, they add up to 10, 5 and 5 add up to 10. And so the mean balances out the deviations, or the distances, from the mean on both sides. Deviations above sum to plus 10, deviations below sum to minus 10, okay? And I think, well, I don't know if this picture is helpful, but a lot of people tell me that they were not, the concept of the mean, which was just add up the values and divide by how many you have, doesn't kind of present this idea of a balance, as far as balancing the distance of their deviations. And I think this also makes sense as far as, if you move the value, one of the values to like 100 or something, that's going to shift the mean because it has to kind of balance those distances. Okay, the other measure of summary values that you learn in your intro stats classes, measures to describe spread. In particular, we have the variance and the standard deviation. And these things measure spread. And so smaller values of variance and standard deviation mean the spread is small, or the values in your data are a lot closer together. So you can imagine something like students in a second grade classroom, what are their ages? In the US in second grade, pretty much everybody is, 7 years old, maybe 8 years old or something like that. So at the start of the school year, you say, how old is everybody in the classroom? Most everybody will say 7, maybe an 8-year-old, maybe a 6-year-old. And so you're going to have very little spread. And so your standard deviation and your variance, those are going to be very small numbers, okay? You're going to have a larger value of variance when you have values that are a lot more spread out. So if you imagine going to the DMV, and there's a bunch of people there, you're going to have lots of different people. You got seniors, citizens, you've got adults, you've got teenagers, you even have like babies of adults and things like that. And so you have a wide range of ages. And so you're going to have a large variance there, okay? Variance, you can think of this as the, quote, average squared distance from the mean, or squared deviation from the mean. And that is, I would put average in quotes there because you add them up and you divide by n minus 1 rather than n. And, but variance is measured in the square of the unit. So if you're talking about distances, your variance is measured in, square meters or square centimeters. And if you're talking about money or something like that, your variance is measured in square dollars, which is a weird concept, and it's hard to kind of wrap our head around. And so the standard deviation will take the square root of the variance, and that kind of corrects the unit. So it's in the same unit that you're accustomed to. So you'd have, standard deviation of the price would be in just regular dollars, not square dollars. And so we often like the standard deviation as well. All right, let's talk about the normal distribution. Normal distribution is, probably one of the most important distributions that we cover in an intro stats class. And the normal distribution is unimodal and symmetric. And we say that that means there's, kind of one peak, and values near the middle are most common, and values that are far away from the middle, those become less frequent, and as indicated by the height of the density curve. And when you discuss the normal distribution, there's often 3 numbers that are presented. This is known as the empirical rule. And we say that approximately 68% of the data is within 1 standard deviation of the mean. Around 95% of the data is within 2 standard deviations of the mean. You know, more accurately, it's like 1.96 standard deviations of the mean, but 2 is a good number to round off to. And then we say around 99.7%. So almost all is within 3 standard deviations of the mean, okay? And those are just kind of numbers that we use for the normal distribution empirical rule. And these are handy to remember. And so maybe you remember these from your intrastats, AP stats days. Maybe not. If not, they're good to commit to memory. Okay, when we start talking about inference, statistical inference, it's important to just kind of get the big frame of reference. And the idea is that, you know, we have some kind of research question, and associated with the research question is a population. The population would be everyone who would be relevant to answering the research question, okay? But the problem with the population is that everyone, when we talk about everyone relevant to the research question, is that the population is too big for direct study, all right? We might not even be able to know how to identify everyone in the population. We might even have a little bit, well, first you have to kind of define who your population is, and that's a difficult thing to start off with. But then, you know, even being able to identify or find everybody in the population is a very difficult thing. So one example here, I have something like maybe your research question is some experimental drug, XYZ, effective at treating disease JKL, okay? The population would be everyone who has disease JKL. But a lot of times you have diseases that maybe even the patient isn't aware that they have a disease, right? So something like cancer, you know, somebody might actually have some form of cancer, but not even be aware of it, okay? And so that person should be included in the population, but nobody knows that this person's in the population, okay? Another major issue of, you know, kind of COVID-19 is that a lot of people are asymptomatic, and so that they are carrying the virus, but have no, don't even know it, okay? And so, you know, identifying this population is a very difficult thing. Defining your population is a challenge as well. And so you can start off with some kind of simple things such as all Americans, all right? You can say like, I want to survey all Americans, but then the question is who actually is an American? And that's a difficult question. Does that include people living, you know, within the United States that are citizens of another country that are not necessarily citizens of the United States? What about citizens of the United States that live in another country? You know, people living in you know, foreign countries and things like that. Do they count? You know, and exactly. You know, who is included in the population is not a trivial question, and is not necessarily easy to answer. So so anyway, that's the population. The population is this big thing. We can't study it directly for multiple different reasons. One being it's kind of too big. And so the idea is in statistics is that we are going to select individuals from the population to be part of our study. And we're going to study the sample, and based on what we see in the sample, we're going to make conclusions about the population. So this is my terrible drawing here. This potato looking thing is supposed to be the population, and it's supposed to represent this large entity that is too big for us to study directly. And so, you know, these arrows show that we've selected individuals from the population and that they are included in our sample. And we are going to study the individuals in our sample and draw conclusions about the population. That's inference. Now, ideally, the sample that we select is representative of the population. That's what we want. We want the sample to be like a miniature version of the population. But that's actually really hard to do. One thing that should give you a representative sample is random sampling. Random sampling is not guaranteed to produce a representative sample. We're hoping that it does, but it is random. And so because it's random, you might select too many of one group of people and not enough of another group of people. That's always a possibility and always a risk with random sampling. And in textbooks, we often talk about, oh, we got some random sample. And it's a very easy thing to write when you're writing a textbook problem and you say like, oh, imagine a random sample of 100 people or something like that. But in real life, it's actually very, very, very difficult, almost impossible to get a true random sample. Sorry. Okay. And so the true true random sample, like if I said, get me a random sample of 100 people who live in the city of Los Angeles, it's impossible. You would not be able to do it, okay? Because first of all, we don't even know who lives in Los Angeles. Like trying to identify every single person who lives in the city of Los Angeles, that's hard. There's a lot of people who have moved recently to LA and nobody knows about that, right? Nobody has necessarily updated the DMV of their new address. There's a lot of people without permanent physical addresses in the city of LA. You know, who exactly counts as somebody living in LA? Like if you have an address, if you have an apartment in LA, but you spent, you know, the last 3 weeks in another city, do you count? So anyway, lots of questions. Getting a true random sample, actually really difficult. Nobody has a list of everyone in the city, but we're gonna ignore that problem for now. We're gonna just pretend that we have some kind of sample, and even if we have a random sample, there's things that are of interest to us. In particular, we're interested in something called the sampling distribution. And so the sampling distribution is the idea that whenever you take a random sample, you might be able to calculate some kind of summary statistic, like, well, what is the mean of this random sample, the sample mean? What's the mean of this random sample, okay? And if two people took random samples from the same population, we would expect their sample means to be similar, but not necessarily exactly the same, right? And some of these, and because there's randomness, it's subject to a random process, there's going to be a probability distribution. Anytime you have basically randomness going on, there's probability associated with it. And so the sampling distribution is basically the probability distribution of all the possible values you can get for the sample mean for all the different possible random samples that someone could draw, right? So somebody could draw this random sample and someone could draw this random sample and get this sample mean and this sample mean and things like that. And so I'm going to kind of simulate the creation of a sampling distribution by doing exactly that. We're going to start off with some hypothesized population. We're going to pretend that there's a normal distribution in the population, and this population has a mean of 0 and a standard deviation of 1. So that we're going to just start off with this standard normal distribution. And we're going to draw a random sample. I think I've done random samples of size 16. And we're going to take these 16 values and we're going to calculate the mean of those 16 values. All right. And I'm going to do this again. I'm going to take another random sample of 16 values, calculate the mean of those 16 values. And I'm going to do this over and over and over and over again. Every single time I'm going to write down the sample mean that I calculate. And at the end, we're going to take a look at all of the different sample means that we've collected. All right. And that'll be the distribution of the sample means. And that will be kind of an approximation of the sampling distribution. And what we'll notice is that the resulting sample means should follow the normal distribution because of the central limit theorem. And the central limit theorem states that if your sample size is big enough, then the sampling distribution of the mean is going to follow a normal distribution. And the standard deviation of that sampling distribution is going to be sigma over the square root of n. All right, so here's just a few pictures. So this is the population, the normal distribution population with a mean of 0 and standard deviation of 1. And here I've drawn a random sample of 16 values. So I got negative 2.21. The values show up here in what we call a rug plot, because these look like little carpet hairs at the bottom of the plot. And so we got negative 2.21, negative 0.84, negative 0.82. So these two lines are very close to each other. Negative 0.63, negative 0.62. Those two lines are like touching each other. We got negative 0.31, negative 0.04, 0.18, things, so on and so forth. And the mean of all of those values is 0.092, and that gets plotted right here. Here's another random sample of 16 values, okay? So this was the first one. Here's another random sample of 16 values, and it gets plotted almost, its mean is very close, 0.096, different values. Here's 16 values, the rug plot changes down here, and the mean is negative 0.197, so the mean changes. Here's another random sample of 16. Here's another random sample of 16. And so we can see these are all different random samples of 16. Each of them have slightly different sample means. And what we want to do is we want to kind of study that. All right. So here I've just written a simple loop. Okay. I'm going to keep track of sample means. I'm going to do this 10,000 times. And so I'm going to say, you know, for I and sequence along sample means, this has a length of 10,000. Take a random sample of 16 values. We'll store that in random sample. Calculate the mean of the random sample, and we'll take the mean and store it into sample means position I. Now I could have combined this line with this line right here, but just for clarity, I say take the random sample of 16 values from the normal distribution first, and then take the mean of the random sample. So here, sample means is going to be a vector of length 10,000 full of 10,000 different sample means. And we can say, well, what is the mean of all 10,000 different sample means? And I get something around 0.0015, negative 0.0015. So I get something very close to 0, which is the population mean. As I would expect something around the population mean. If I did it for more than 10,000, maybe like 100,000 or a million, I'd probably get something even closer to 0, but I didn't feel like running the simulation that long. And then if I calculate what's the standard deviation of all of these sample means, we get something very close to 0.25, okay? According to the central limit theorem, we should get sigma divided by the square root of 16. Sigma is 1, square root of 16 is 4, 1 over 4 is 0.25, and indeed I get something very close to 1 over 4. All right, and here's a plot of all of the different sample means that I collected. There's 10,000 of them here. And indeed, it looks a lot like the normal distribution, maybe not perfectly so, but something very, very close to the normal distribution. If I kind of ran it like a million times, I'd probably get something even more close looking to the normal distribution. Here's just a QQ plot, and it looks normal. We've got a pretty straight line there. Oh, and the kind of the key idea is here is that, you know, if your sample is large enough, then the central limit theorem says that the mean of a random sample is going to come from a normal distribution, and that normal distribution is centered at mu, which is the population mean, and the sampling distribution is going to have this standard deviation sigma over the square root of n, which is, you know, what we call our standard error. And so, you know, according to the normal distribution, we know that 95% of the time we're going to be within 2 standard deviations of the mean. So that means, you know, a random value drawn from the normal distribution will be within 2 standard deviations of the mean. And so if we combine this idea with this idea, what we're going to say is that if I draw a random sample, there's a 95% probability that the mean of the random sample is going to be within 2 standard deviations of the population mean. Okay, so that's what we have. 95% probability that the mean of the random sample will be within 2 standard deviations of the population mean. And so we can take that idea that saying, like, if the population mean is here, there's a 95% probability that a random sample is going to be within 2 standard deviations of this population mean. And now we're going to say, well, if I observe a random sample here at X bar, I can be 95% confident that the population mean mu is within 2 standard deviations of X bar, okay? The analogy I use is kind of like that of a boy and a dog. You can imagine, you know, there's a boy and his dog is his best friend, and wherever the boy goes, the dog kind of follows along nearby. And so we're going to say 95% of the time, the dog is, you know, within, you know, I don't know, 2 yards of the dog, of the boy or something like that. And so if you see the boy, you know, there's a high probability that the dog is nearby. One day, let's say you spot the dog, okay? And if you spot the dog, you can be confident that the boy is also nearby, okay? Because we know that the dog kind of follows the boy around. And so if you do see the dog, you can be confident that the boy is around nearby. And so similarly, we know that sample means X bar are within 2 standard deviations of the population mean 95% of the time. So whenever we spot an X bar, we can be confident that the population mean is somewhere close by. And that's the situation that we're in when we do, when we take data, is that we can't study the population directly. So we don't know where mu, the mean of the population, is, but we are able to observe a sample. We are able to observe an X bar. And so because I'm able to spot X bar, I can be confident that the population mean mu is somewhere nearby, even if I can't observe the population mean mu directly. Okay. And so that forms the foundation of the confidence interval. We can be, you know, confident that the mean mu is within 2 standard deviations of X bar. But the only problem here is that this quantity, sigma over the square root of n, is unknown to us. We don't know what the population standard deviation sigma is. And so what we do is we're going to estimate the standard deviation of the population using the standard deviation of the sample. We're going to use S, our sample standard deviation, as an estimate of mu. But when you do this, this introduces extra uncertainty. And so to kind of balance out that extra uncertainty, instead of using the normal distribution, we use the t distribution, okay? And the t distribution is pretty much like the normal distribution, but you've got the degrees of freedom parameter, and it kind of just spreads out the normal distribution a little bit. And so you don't use 1.96 standard deviations, you use something a little bit bigger, you know, 2.102 or something like that, depending on your degrees of freedom. And so your confidence interval ends up being like this: X bar plus or minus t times S squared n. So I think you guys in 100B have to derive the t distribution, and, you know, you learn about the relationship. It's the, you know, a standard normal z divided by, you know, the square root of a chi-squared type of thing, variable. Did you guys also learn the history of the t distribution, where it was from William Gossett, who worked at Guinness Brewery? You know, they make beer in Ireland, and he was in quality control for Guinness Brewery, and, you know, he was like rejecting these batches based on these samples, and they said, you know, you got to be doing your math wrong or something, because these things were fine. And so he revisited the thing and realized that, you know, he was using the normal distribution. His calculations are based off the normal distribution. They needed to be based off of a different distribution, and so he figured it out, and that's the t distribution. So anyway, we can wait. I forgot. I have to give you quiz answers. Have I given you a quiz answer yet? View quiz answer? 0? None of them? Oh man. Okay. Let me give you. I'll give you 2 right now. First 2 view quiz answers are A and C. A as in apple, C as in cat. A as in apple, C as in cat. Those are your first 2 view quiz answers, okay? A as in apple, C as in cat for your first 2 view quiz answers. All right, so we can take another approach for statistical inference, and that's going to be hypothesis testing, okay? And so when you do hypothesis testing, you create these hypotheses, which is basically you're defining these hypothetical what if scenarios. And we're going to say, what if there is a population and it's got this mean and it's got this standard deviation, And if that were the case, you know, this hypothetical what if situation, if that were the case, what is the probability it would produce the sample that I have? Okay, what is the probability that it's going to produce the sample that we have? And we use that to kind of inform our decisions about, you know, is my hypothetical situation, this what if scenario, is that a realistic scenario? Okay, and so one of the most basic hypothesis tests that you learned, I'm sure, in your intro stats and your AP stats class is the two independent sample t-test. All right, and what this does is it says you've got two populations. You got population 1, you've got population 2, and you take a sample from population 1, you take a sample from population 2, and based on the sample 1 and sample 2, you want to say, well, do the respective populations, do those have the same mean, or do these two samples, are they different enough that we can say that the two populations have different means? And so your null hypothesis starts off with kind of this hypothetical situation of kind of, let's assume, what if that there's these two populations that we're drawing from, these two populations have the same mean, okay? That there's no difference between the mean of population 1 and the mean of population 2. And if that were the case, if I observe a sample 1 and a sample 2, and there's a difference between sample 1, the mean of sample 1 and the mean of sample 2, that difference can be explained just from the random sampling process. We can say, you know, when you take a random sample, you're going to get slightly different samples. And the fact that this one ended up with this mean and this one ended up with this mean, that's just due to random sampling, okay? And the p-value is, you know, we're going to calculate this out. This is going to be the probability of observing some summary statistic that's equal to or more extreme than the summary statistic that we observed if we assume the null hypothesis is true. So, so again, we start off with kind of this what if scenario. We're going to say, what if the two populations have the same mean, right? And if the two populations are assumed to have the same mean, whenever you take two random samples, you expect the two random samples to have means that are approximately equal. Maybe not exactly equal, but we would expect them to be pretty close to equal. And there's no reason to expect one to be greater or one to be less than the other. So we're going to expect it basically a difference of 0. Okay, we're not expecting it to be exactly 0, but overall we're expecting a difference of 0. And then, so let's say you go out and you collect data, sample 1, sample 2, and they don't have a difference of 0. I think on the next slide, I've got, you know, sample 1 has a mean of 10 and sample 2 has a mean of 12 or something. You got a difference of 2 between your two samples. Okay. And the question is, if the two populations actually were equal, the means of the two populations actually were equal, then what's the probability that random sampling would produce two samples where the difference between them is something like 2 or something even more? Because that's what we got. We got a difference between our two samples where the mean is, where the difference between the means is 2. Is that likely to happen? And the answer is well, it depends. It depends what else the data says, right? And so in one scenario, what if you go and you look at your samples and your samples have very little standard deviation, right? Sample 1 has a mean of 10. And if you look at the values inside of the sample, let's say they're like 10, 10.1, 10.2, 9.9, 9.8, 10.0, things like that. They're all very, very close to 10. You look at sample 2 and their values like 12, 12.1, 11.9, 11.8, 12.2, values that are very close to 12, okay? And in that case, we would say, you know, the mean of 12 here and the mean of 10 here, that probably can't be explained just from random chance alone, right? That this difference of two points is something significant, okay? On the other hand, you could take a closer look at your samples, and maybe the standard error is large, right? You look at this sample, the values are like 5, 10, 15, 0, and 20, and they average out to a mean of 10, okay? The other one, you've got, you know, 2 and 12 and 20, whatever, 22 and 15 and 7 or something like that. you get another set of values, and the average happens to be 12. But you know, the values are quite all over the place, you know, ranging from 0 to 22 and things like that. And so in that case, a difference of, you know, 2 points on average, you know, might not be that big of a deal. Okay. So in that case, we would say this difference of 2 points doesn't seem that significant. Okay. And so, you know, you end up going through a bunch of kind of calculations, and you end up calculating the p-value. The p-value, again, quantifies the probability of observing your data, or something more extreme, if the null hypothesis were true. And you compare your p-value to some arbitrary significance level, alpha. Okay, often we choose 0.05, but that's an arbitrary number. You pick whatever you want. Okay, and you decide if your p-value is large or small based on that. And so if your p-value is small, you reject your null hypothesis. Okay, small p-value means that according to the calculations, if this were a hypothetical situation, there should be a very low probability of getting, you know, a difference of 2 between the samples. All right, if hypothetically, if the populations had equal means, it says there's a very low probability that you're going to get one sample where it's 10, the other sample it's 12. But that's what happened. That's what happened in our data. So the fact that we observed this data tells me that my hypothetical situation is wrong, that this null hypothesis is wrong. Okay. All right. On the other hand, if we get a large p-value, then that means, you know, under a hypothetical situation, yeah, we're expecting samples where the means are very similar to each other. But we did the calculations and says, oh, you know what, difference of 2, that could happen. You know, we might get differences of 2. We might even get differences of 5 or 7 or things like that, according to this hypothetical situation. So difference of a 2, that's not even that big of a deal. So, so there's no reason to really doubt the hypothetical situation, because the hypothetical situation says, yeah, you can get things like differences of 2 or 5 or 7. So you got a difference of 2, not that big of a deal. You're not going to reject the null hypothesis. Okay. I hope in your intro stats class, they told you should never say the words, we accept the null hypothesis. Okay, we accept the null hypothesis is something that we're never allowed to say as statisticians, because we'll never be able to actually prove that the null hypothesis is true. All we can say is that we have data, and the data does not contradict, or, you know, is not in conflict with the null hypothesis. All right, so these hypothesis tests, the t-test that we talked about, that's what we call a parametric hypothesis test, because it's based on the normal distribution. It's based on the central limit theorem and those kinds of ideas that, you know, you probably had to prove in your 100B class. And what we're going to do next week is we're going to take a look at some randomization tests. Okay, randomization tests don't make assumptions about the sampling distribution, and we don't have to say that things follow a normal distribution and stuff like that. But we there's a different assumption that we have to make, and it's going to be kind of depend on this assumption of exchangeability. And I'll talk about that next week. And so we'll discuss that. With our remaining time, I want to do a quick review on data collection, because that's going to have implications for the kinds of conclusions that we can make, right? And so as far as data collection goes, there's kind of 2 key ideas. There's the idea of random samples and random assignment. And whether random samples or random assignment was used is going to impact what kinds of tests we can conduct and what kind of conclusions we can make. And so here's just some hypothetical scenario. This says, suppose a dentist wants to know if a daily dose of vitamin C, 500 milligrams of vitamin C, will result in fewer canker sores than not taking vitamin C. All right, so this is some silly question. I want to know what this happens. Okay, scenario 1, basically, we're going to start off, we're going to convince all the dental patients in our town that have appointments in the first 2 weeks of December to be subjects of our study. And then we divide them into 2 groups, those who take at least 500 milligrams of vitamin C every day and those who do not. We ask them questions about their canker sores, and we check their dental records. And then at the end of the study, we compare the proportions of those who take vitamin C and complain about canker sores with the proportion of those who don't take vitamin C and have canker sores. And we find out there's actually a significant difference between the two proportions. And the people who took vitamin C have fewer canker sores. So what can we conclude? Well, the issue is that our data set is not a random sample. We selected everybody with the appointments in the first 2 weeks of December. That's not going to be a random sample. And I don't know what might correlate with having appointments in the first 2 weeks of December, but you know, there could be something there. All right, and it's not a random sample. And so we're not going to be able to generalize this to the larger population, okay? Unless you make some major assumptions like the sample that I have is representative of the larger population of all dental patients or the larger population, you know, but those are like very major assumptions that could very well be wrong and be bad, okay? The study is also observational. We did not say you must take vitamin C and you must not. We just asked them, do you take vitamin C on a regular basis? Yes or no? And some people said, yeah, I do. And others said, no, I don't. And probably people who take vitamin C supplements are more likely to take other kinds of supplements as well. Okay. And so perhaps the people who take vitamin C might also be taking vitamin B, and maybe vitamin B is the thing responsible for a reduction in canker sores. Okay, so we don't really know. So it's hard. So we can't make a conclusion as to why we're seeing a reduction in canker sores. So all we can say is that for these patients, those who take vitamin C have fewer canker sores than those who don't. We don't know why. And we don't know if this would generalize to another group. Okay, scenario 2, we're still dealing with the same patients who have appointments in the first 2 weeks of December. So this is not a random sample. But we randomly assign some of them to take vitamin C and some not to take vitamin C. And then we meet up with them 3 months later and we check and there's a difference. Okay, so again, same problem as before. It's not a random sample, so we can't assume that it's going to be representative or hold for a larger population. But the treatments were randomly assigned, so the difference in proportions can be attributed to the vitamin C, okay? Because we use random assignment, and we can say, you know what, some of them we randomly said take vitamin C, others we said not to take vitamin C. And so if we are observing a difference, and it's a statistically significant difference, that difference can be attributed to the vitamin C that was used, okay? But again, we don't know if this would be consistent with another group, but we believe we know why for this group that the proportions differ. All right, scenario 3, we select a random sample of dental patients in the town. So I don't know how we did this, but somehow we get a random sample of dental patients. We don't have random assignment of treatments, okay? And then we study and then we see there's a difference in proportions, okay? It's a random sample of patients in the town, so we can at least generalize to all of the dental patients in the town, okay? So we can infer that the results obtained in the study would be consistent with results from the whole population, and the population in this case would be all dental patients in the town, okay? It's observational, so we can't make a cause and effect conclusion. But again, we're dealing with dental patients, so we can't just conclude generalize to the general population of all people, okay? We can only generalize to people who are dental patients, which, you know, maybe these are at least people who visit the dentist, and that says something to start off with, okay? We might be able to make a few more assumptions, but again, these are, every time you make more assumptions, you run the risk of being wrong, right? So if you say your town's dental patients are representative of all dental patients in general, then you can expand your conclusions and things like that. Okay, but that's a risky assumption to make. You know, a lot of times you'll see medical studies, and the medical study might have been conducted in in England or in Great Britain, or it might have been conducted in another country like China or Japan or something like that. And generally the people who participate in that medical study will be from some local hospital or something like that. All right. And so there are often just health and cultural and dietary differences from one nation to another, right? The diet of the people of Japan probably is not the same as the diet of people in the United States. And so whatever conclusions that they make in this study of, people in Japan or China or Britain or the US may or may not be able to be generalized to the rest of the nation, or not the rest of the nation, the rest of the world and things like that. And so these are questions that that we have to kind of keep in mind. And we always have to ask, is this population that was studied, or is this sample that was studied, is that representative of the population that I want to generalize to? And maybe it is, right? If it's just kind of like something that's humans in general, maybe. But if things like diet, and diet almost always plays some role in health analysis. So who knows, right? So it's those are things that we got to kind of consider. Okay. All right. Scenario 4, we're going to have the random sample and random assignment. And if you have random sample and random assignment, then you can generalize to a larger population, and you can make a conclusion about cause and effect. All right. And that's pretty much what all this says. Again, we can generalize to the population from which our sample was drawn, which was dental patients, right? So we have a random sample of dental patients, so we can generalize to all dental patients because it was a random sample. And again, because it was random assignment of treatments, we can make a conclusion about cause and effect, all right? But the reality is that this scenario of having random assignment and random sampling is like a fantasy scenario. This almost like never happens in real life, right? As a statistician, it's like fun to dream about fantasy scenarios of data collection, but getting a random sample is very difficult to do. And then having random assignment with a random sample is almost unheard of. And so usually you have to kind of pick one or the other, because when you do some kind of study, an experiment where there's random assignment, you need to get participant consent. You have to say, are you willing to participate in this study? And and the study could be something like, we're going to give you a placebo, or we're going to try out this medication that's so far untested, and there's unknown side effects, and so it could possibly be harmful to you. Like, we don't expect it to, right? Like that, you're not allowed to, like, for ethical reasons, you're not allowed to do an experiment where you expect negative things, right? But you're saying we're expecting positive things, but we also have to acknowledge there are risks of side effects. And when you say that, people decline and say, I don't want to participate. And if somebody declines and they don't want to participate, then it's no longer a random sample. And you're going to have basically, generally, people with lower risk tolerances are less likely to participate in your study. And if there's something related to risk tolerance, could have an outcome on the thing, this may or may not, this conclusions you draw, well, they're certainly not a random sample and things like that. Okay. And then, as far as getting a random sample, that's also difficult to do, right? So, maybe you've gotten a phone call from a survey company trying to conduct opinion polls and things like that. And they always ask, like, do you have 10 minutes to participate in a survey? And not everyone's going to say yes. And so, the people who do respond want to, I'm always baffled whenever I go on Facebook, which I don't go on Facebook anymore, but or go online and stuff. I'll see people say like, hey, fill out this survey that I put on Google Forms. And I'm just always questioning, like, how can you expect anything that's even reasonably accurate or helpful from a survey that you conduct on Google Forms? There are people who delight in filling out fake responses in Google Form surveys to mess up the results of a poll. And you know, there's no way you would even know that if your sample of data that you've collected is going to be representative. So anyway, these are getting a real good data set is really hard. When you take 101B next quarter, there's a possibility you have to do an experiment on the island, where it's a simulated experiment where you have to collect some data. And you'll find that the data collection process, just that island, and they purposely makes some of the data collection like a little bit frustrating and a little bit tedious, and that so you don't have, nobody says like, I'm going to just collect data from 1,000 people, because that might take like hours, days of work to just collect that thing. So you might have to settle for having like 50 observations, and even that will be a lot of work to collect. And the point of the class is to come up with a study so you can get the most information out of whatever sample of data that you have, because it's expensive collecting real data. Like a medical study, each observation, each participant is usually thousands of dollars of investment of time and resources to get a single observation. Okay, anyway, let me give you your last view quiz answer. Last view quiz answer is the letter B. B as in bear is your last view quiz answer. B as in bear. Okay, so we'll end here for today. Have a good weekend, you guys, and we'll see you guys on Monday, week 9. Have a good night.